Well, here comes section 2.4. It's called the precise definition of a limit. Let me just give you an idea of what this section, what's coming. Usually when I teach this class in 2.2 and section 2.3, there's a lot going on there. There's a lot of different ways to approach different kinds of limits, right? Can you just plug it in? Is there a hole? Is there a vertical asymptote? The different algebra techniques. But generally students, they feel all right about it coming out of 2.2 and 2.3, especially once they've had a chance to do some homework. And then comes section 2.4, and it tends to really be difficult, a very challenging conceptually section. There's not a whole lot of algebra here, but just the concept of the precise definition of a limit is really pushing the rigor pretty heavily. So I'm going to try and ease us in as gently as I can for one. So I'll just tell you that. But also keep in mind this section is what we call a standalone section. Nothing we do in the future is going to build off of this section. It just is what it is. And then we move back to the less precise definition of a limit that we've actually been using so far. And you think, well, why should we even cover this section? People who become math majors need this section because you're going to see things in future math classes that are going to build off of these ideas. And if you haven't seen this now, you're really going to be behind the other folks taking the class with you in the concept. And whoever might be teaching those classes is going to expect you to have seen this before. So if there's even a possibility you might be a math major, then this is for you. And there's a chance some non-math majors are going to encounter the ideas that come up here as well, but definitely the math majors. Now, we all understand that very few people become math majors, just out of the whole, population of students. Well, sorry for the rest of you. You got to sit through it because we can't slight the people who might become math majors later on. So we all get to learn it, and that's just the way it goes for you guys. That said, depending on who you take for Calc 2 or Calc 3, some of these ideas might very well come back in those later calculus courses. Kind of depends more so on the teacher and how precise or rigorous they want to be at that point. So it could very well come in handy for almost everybody, but definitely for the math majors. Okay, so what is this all about? Enough talk. The precise definition of a limit. So here's the definition that we've been working with, and I'm going to call it the working definition, the less precise. Here's what we've been saying. If as x approaches a, f of x approaches L, then we say the limit of f of x as x approaches a equals L. And so we use this sort of language before with approaches, right? Certainly it's the same notation. The key word there, right, was approaches. As x approaches a, f of x approaches L, then we say the limit of the function as x approaches a simply equals L. Okay, that's what we've been working with. That's a great definition for getting things done, but you notice something about this, and I'm going to sort of draw this out. Let's look at an example with some actual numbers, and I think that will be easier to wrap our head around. Let's consider this. The limit of 4x minus 1 as x approaches 2, and I've already telling you what that equals. In this case, we could just plug the 2 right in. That limit would equal 7. Okay, so now we have a function, 4x minus 1. We have a value for x, and the limit value, 7. Okay, so what does this mean? So this is the way we thought of it before. The less precise definition, as x approaches 2, 4x minus 1 approaches 7. Again, we don't care what happens when x actually reaches 2. We don't even care that when we plug in 2, we get 7. Really, when it comes to the limit, it's as x approaches 2, that function approaches the y value of 7. Okay. Why is this not very precise? It's this word, the very word that makes a limit, the approaches, is not, we'd say, it's really not a very mathematical word. It's not well defined. Why not? What does it mean for x to approach 2? So somebody might say, well, like 2.1. 2.1 is approaching 2. Or maybe from 2.1 to 2.01, you know, you're definitely getting closer to 2. You're approaching, or maybe 2.001, you know, you're approaching 2, that progression. And somebody else might come and say, wait a second though. How many values are there between 2.001 and 2? Right? How can we say that 2.001 is approaching 2? There's still infinitely many values between 2.001 and 2. Who knows what might happen in between if there's infinitely many numbers there? Who knows what the function, what the behavior could be like? And so to one person, maybe that's you're getting close enough, but somebody else could say, well, but there's still, and even if you went further and further, right, there's still infinitely many numbers still left before you actually reach 2, where who knows what could happen. Same thing on the function side. As this approaches 7, okay, so you might be getting closer to 7, but however close you get, there's still infinitely many numbers between that and 7 itself, and who knows what might happen. So what's approaching to one person, somebody else could easily disagree. You're infinitely far away, you know, they might say. Okay, so this kind of like sparks like, oh yeah, that's true. Okay, so this is the question I wrote out. But how close must values be, either to 2 or to 7? How close must we get to approach? And we don't have a good answer for that because the word approach is not precise. Okay, so here's what we're going to do. We're going to rethink this. We need specific distances from 2 and from 7 to make this precise. So we're going to say, hey, if you get to 2.1, then that's a specific distance. You're 0.1 away from 2. You could kind of argue the same thing on the lower end, like 1.9. You know, if you get within 1.9 to 2.1, if you're that close to 2, then you're within this certain distance, and we can agree that, you know, you're approaching. Or the same thing with 7. If you get within a certain distance specified beforehand, then we'll just all agree that that's as close as you need to get, kind of an idea. Okay, so we need specific numbers, distances, from these two values, 2 and 7. So let me show you what that looks like. I'll pick a number, a distance. Here's what we're going to do. Kind of, again, we're just building our way up to the precise definition of a limit. We still have a lot to talk about, a ways to go before I tell you what that definition is. We're just working up to it. Okay, this is what we're going to say now. How close must x be to 2 so that 4x minus 1 is within 0.1 of 7? Okay, now there's no arguing this question and what it means. This is very well defined. It's very precise. I want my function to be within 0.1 of 7. Okay? So how close do I need to get x to be to 2 to make that happen? There's only one answer to this, right? We can figure out what that x value is. Okay, how are we going to do that? Okay, so let's look at what we're told. We want our function, 4x minus 1, to be within 0.1 of 7. Let me slide this up. So that means if it's within 0.1 of 7, it could be either direction, right? A little bit lower or a little bit higher. So I'm going to say this right here. If we're within 0.1 of 7, then our function is going to be caught somewhere between 6.9 and 7.1. If it falls in between, then we know, no doubt about it, it is within 0.1 of 7. And also keep in mind, these are strict less thans. We do not allow it to be exactly 0.1 away from 7. It's got to be within. So we just use the less than signs, not less than or equal to. Okay. So if we get within that little window, then we're definitely within 0.1 of 7. So what are we after? We want to find what x value makes this happen. Okay. Well, hey, we've got this inequality set up. We can figure out what x is. We'll isolate x in the middle, and we can get it. So with this triple inequality, we can add 1 to all three. Okay. Adding 1 to all three, well, that'd be 7.9 less than 4x, less than 8.1 if we add 1 to all of them. Then we'll divide them all by 4, and we'll get x there in the middle. And it turns out when you divide 7.9 by 4, you get 1.975. And when you divide 8.1 by 4, you get 2.025. Now notice what happened. The x value, that's a little bit less than 2. That's a little bit bigger than 2. So let's look back to the question. How close must x be to 2? Well, how far are these numbers on the outsides? How far are they away from 2? And it's a little bit clearer to look at the bigger one. It's 0.025 away, but that'd be the same down here. That's still 0.025. So we can say, with no ambiguity, that x must be within 0.025 of 2. And we've answered the question. There's no doubt about it. If we get x to fall within this little window, then our function will fall within this window. And nobody can argue that. Okay. So what I'd like to do is restate that same question that we just answered. But we're going to do this, we're going to solve for x a little bit differently. The way we did it before, it worked fine. Obviously, we got to an answer. But if we showcase this a little bit differently, we'll actually work for a more general approach. Okay. So I'm going to restate this. It's the same question as a moment ago. How close must x be to 2 so that 4x minus 1 is within 0.1 of 7? So instead of saying that 4x minus 1 is between 6.9 and 7.1, I'm going to do it this way. Okay, so I've got these absolute values, all right? And I'm saying 4x minus 1 minus 7 in absolute values is less than that distance 0.1. And now it might take a moment to kind of absorb that this means the same thing as that statement back the way we began the previous example, or the previous question. But let's think of it like this. So what we're really saying here, when we take the difference, when we subtract there, we're saying the distance between these. The distance between 4x minus 1 and 7. Okay, the distance between those is less than 0.1. And I take the absolute value because this might be a little bit bigger than 7. It might be a little bit less than 7. I always want that to be positive because I'm talking about a distance. So here's kind of what I just said written out. The difference between my function 4x minus 1 and 7, the difference, right, subtract, the difference between them is less than 0.1. And I take the absolute value because I don't want to think of the distance between them as being a negative. Distance is always positive. Okay, hopefully it'd be a little bit easier if we were in class and I could, kind of get a sense of whether you guys are on the same page with me. But that's not the case. So I'm going to continue on. What are we going to do? We're going to simplify this. We're going to work with this side. We're going to get to the same answer we did a moment ago. Let's take a look at this. Okay, we simplify, right? So we got 4x minus 8 less than 0.1. All right, well, that's no big deal. Next, we're going to factor out a 4. There's a 4 in common here. We can factor it out, and because it's positive 4, we can actually move it all the way outside the absolute value. So when we factor out that 4, we're left with absolute value x minus 2, still less than 0.1. And now let's divide that 4 over here. And you see a familiar number. When we divide by 4, we've got the absolute value of x minus 2 is less than 0.025. And that's the same answer we came to a moment ago. And what's kind of nice is, about this form, about this style of approach, we see the answer right there. We don't have to go back and think, well, how far is that from 2? Or it was 2, right? We see the 2 right here. The difference between x and 2 is less than that distance, 0.025. So at the beginning, it takes the same form as the end. The difference between the function and 7, we want it to be less than 0.1. We end up with the difference between x and 2 is less than this number, and that's what we were after. Okay, there's still more to chat about before we get to that precise definition. Check out part 2 next.